Okay, class, now this topic is tangent lines. So we're interested in this red tangent line, which in our story was the, at south of the border, the police officer was aiming a radar gun at us, and that radar gun will give us an instantaneous speed. At the moment we cross south of the border, it'll tell us exactly how fast we're going. And that has something to do with the tangent line, but we have to figure out how to get the slope of this tangent line. And so a couple things about a tangent line. So we had this thing, secant lines, average rates of change, they go between 2 points. Well, this tangent line only touches your function at 1 point on the curve. This red point, the point of tangency. And so how will we get the slope of a line when we only have 1 point and the slope function involves 2 points? That's a dilemma that we have to resolve in order to get the slope of this tangent line, right? I need another point, and all I have is this black function, right? And I only have 1 point on that. So our goal by the end is to figure out the slope of the tangent line. And we're gonna eventually learn that a tangent line the slope of a tangent line, as opposed to a secant line, is going to give us an instantaneous rate of change of y with respect to x. So just like with the average rate of change, our units would be the same. In this case, y is in miles, x is in hours, so it would be miles per hour. And so in this scenario, if we could get the slope of this tangent line, it'll give us an instantaneous speed, that radar gun speed that we desire. And hopefully it makes sense, this average idea versus instantaneous should be clear, because the secant line, again, is between 2 points over some duration. That's where the average part comes in. As opposed to instantaneous, the tangent line has a point of tangency. It only touches at 1 point, 1 instance. So it should be clear again that the slope of the tangent line will give us an instantaneous rate because it only touches once at 1 instant. Okay, so it's going to take us a while to come back to the south of the border time and border problem and figure out exactly how fast we were going there. And for the moment, we're going to now get good at estimating tangent lines, like figuring out how to draw them on a function. So we'll make some space and make a different function. Still keep our 2 properties here. Those are important distinctions between our 2 types of lines. Let's just say we have a function that looks something like this. Y is a function of x. Clearly a nonlinear function, right? Also continuous, I can trace it without picking my pencil up off the paper. No holes, jumps, asymptotes, no breaks. Okay, so again, what we're going to try to do is talk about how to estimate what a tangent line is. And let's say we stop right here, and that is our point of tangency. And we want to get good at just estimating what a tangent line is. We'll ultimately figure out how to get it exactly, but it'll really help us with our concepts if we originally spend some time figuring out how to sketch a tangent line. All right, so one way of thinking about a tangent line is that this function is really like a particle moving through space. And in this case, it's a 2D plane. And this particle, maybe moving over time, is tracing out this nonlinear function. And you could imagine another way of thinking about this is maybe that this function is like a roller coaster. Well, when I stop at a point of tangency, it's as if I was going on the roller coaster, riding along, but at the point of tangency, I would sail off and I would travel in the direction of motion. So the direction of the particle if it's moving, or you being on a roller coaster. If it were to derail right here, the roller coaster would continue moving in this direction. So let me draw that as a line. That is the tangent line. And the tangent line has both a forward direction and a backward, as if I was riding the roller coaster in the backward direction. And for my East Coasters, in the amusement park, Kings Dominion used to have a roller coaster called the Rebel Yell that you could ride forward and you could ride it backwards. So if I was riding in the backwards direction and I derailed right here, I would sail off. And again, that should make it will always make a straight line, that is called a tangent line. So let's just practice putting a couple other tangent lines. I'll pick a few other points, maybe here, 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 and there. Okay, so pause the video, take a moment, sketch this on your notebook, and try to draw the tangent line at these 4 points. Okay, so you come back from that. Let's see if yours check with mine. So I'm riding along, imagining this is a roller coaster. It derails right here now at this point of tangency. And I would sail off in this direction. And there's my tangent line. The next one, I would sail off, and it would really look pretty much like the function actually. Here, it's actually kind of level. And last one there. So some things that you notice from drawing this is at any point of tangency, you can draw a tangent line. And the slope of that tangent line depends on the point you're at on the function. So again, any point, there's infinitely many points along this line. I could stop, call that my point of tangency, and draw a tangent line. And we're using the idea of thinking about the function as a roller coaster or a particle moving through the air. And this would be where we derail, or the direction of motion. So the tangent line gives the direction of motion of your nonlinear function. And that matters, again, depending on where you are. If you just have a linear function, things aren't as interesting, right? My direction of motion along a linear function at any point is always exactly the same. The tangent line is the line, right? Not very interesting to get a tangent line. But on a highly nonlinear function, it is interesting because the tangent line gives you quite a bit of information. We're going to get into that particularly in chapter 2. For now, the key piece of information that it's giving us is that it is a direction of motion. Now, another way to draw a tangent line, so if that understanding of the tangent line is still a little fuzzy, maybe this will help. Another way of thinking about a tangent line, draw a function. Y is a function of x. We now know what that means. Y depends on x. Give me an x, I'll plug it into the function rule, it'll spit out a y. And another way of trying to draw a tangent line at this point here is to use the idea of a linelet. So, key term. Early mathematicians who invented calculus, there was a guy named Isaac Barrow, and he had the idea, again, that this is really like a particle. This function really represents a particle moving over time. And he talked about the direction of motion, but he also talked about the fact that no matter how nonlinear a function was, if I zoom in on it, maybe on this section of it, and then I zoom in even more on this section and this section, just getting tighter and tighter around that point of tangency, the function actually looks like a straight line right there. And then if you just extend that little linelet, it becomes the tangent line. So the idea of zooming in and zooming in and zooming in is another way to estimate drawing the tangent line. So right here, I can imagine zooming in, zooming in, zooming in on this nonlinear function. The closer I get, the function looks less and less nonlinear and more linear, just in that tight little section. And you can think of a function, like Barrow thought about this nonlinear function, is really made up of tiny little linelets, like infinitely tiny little teeny straight lines, right? And he just thought the whole function was made up of those. And if I just made them small enough, I'd get an idea of what the tangent line looks like at any point. Okay, so you have some activities in your book that you're gonna work for homework and practice. Make sure you can draw tangent lines, you can sketch a tangent line, and then we can figure out some information from that tangent line. And we'll come back to our south of the border point for a moment in a bit. For now, let's see what does this tangent line tell us. So there's a few things that a few pieces of information that we can get from the tangent lines drawn in this picture here. I can't tell you exactly what the slope of this line is because I don't have 2 points to get that formula, change in y or change in x, but I can tell you some information. Like for instance, I know that this line has what kind of slope? Is it a -0 or positive slope? We see, just by looking at it visually, right? Any line leaning like that is a positive leading line. This has to have a positive slope. So the slope n is positive. Over here, slope is negative. Slope is positive. This one looks completely horizontal, 0 slope, negative slope. Oops. So we can get an idea of whether or not our slope is positive, negative, 0 at tangent point, using the tangent line at a point of tangent C, and we can figure out that. But what does it mean when the slope is positive, when the slope is negative, when the slope is 0? What happens? So let's think about this again as a function, and maybe this time we're pedaling a bicycle along this function. What happens whenever we have a positive slope? So let's maybe add a few more points of tangency. A few more tangent lines. Is it true that on this section, positive, positive slope, positive slope, positive slope, all of those had positive slopes? The tangent lines always had positive slopes on this section. And then I reach a peak, and then I start coming with my tangent lines. Draw a tangent line there, draw a tangent line there. Every single one of those is negative leaning, right? It's got a negative cant to it. So these are all negative, negative, negatives all the way down. Now think about, again, this is a function I'm pedaling a bicycle up. What does it mean when you have a tangent line with a positive slope? It means you must be pedaling uphill, right? And then as soon as it switches to a tangent line with a negative slope, you must be pedaling downhill. And then I'm back uphill. And then precisely at this point, I'm neither uphill or downhill, I'm just paused for just an instant, just a split second, I'm paused, stationary, and then back downhill, back uphill. And so we're going to make this connection. Also has to do with the tangent line. If the slope of the tangent line is greater than 0, so positive, what can we say about the function? The function must be increasing. Which just means as I ride from left to right, and x is always moving positively in this direction, as I move along the domain from left to right, when the function is rising, the values are increasing. I have an increasing function till about here, and then it's decreasing when the slope of the tangent line is less than 0. Our function is decreasing. When it's exactly 0, it's neither increasing nor decreasing. And we say that the function has a horizontal tangent line there. And those are going to be really key points for us. Places where we have horizontal tangent lines. They're going to be so important for us that we're going to call them critical points. They're critical, right? So these are eventually going to be called CPs, critical points. Okay, so let me summarize a few things, then we'll set up for the next video. A tangent line touches your function at one point locally. It's okay if this tangent line, like, let's see if we have an instant here, like this one here. If I extend it, it's going to go ahead and touch over there. But I want the slope like zoomed in close. It only touches it once there, right? Okay, so, and then the slope of that line represents an instantaneous rate of change. You can get the slope of a tangent line. You can estimate it visually, whether it's positive, negative, 0, at any point on a curve by thinking about two ideas. By thinking about this curve as like a roller coaster, and the point of tangency is where you are to derail, and it's your direction of motion. Or the second idea is thinking about this curve as made up of a bunch of tiny little line segments called linelets. And as you zoom in closer and closer and closer, the nonlinear function at some point of tangency looks like a tiny little linelet. And then you extend that tiny little linelet into a line, and that is a tangent line. If the tangent line is leaning this way, it's a positive sloped line, and so therefore the function is increasing at that point. Any points that have a positive sloped tangent line means the function is increasing. On the other hand, if the slope of the tangent line is negative, you have a decreasing line. And lastly, at those rare points where the slope of the tangent line is exactly 0, you have a horizontal tangent line, completely horizontal. You're neither increasing nor decreasing there, and you're something that we're going to call a critical point. And that adjective is important. It's critical. We're going to use them so often in this class. Okay, so last thing before we move on to our next topic in the next video is the south of the border story. So just want to set up some ideas there. So we had a function that looked like this. We were traveling from Charleston to Raleigh. We were going kind of slow at first, and then we started to really speed up. We knew that over the second half of the trip from south of the border to Raleigh that we were really going 80 miles an hour, because this was the point 4280. This was the point 2120. This is the point 00. And really what we're interested in, our goal, the next video, is to figure out how to get the slope of this tangent line. You can sketch the tangent line using those two ideas of direction of motion, or using it as zooming in with the linelet. You get this red tangent line. We do see that it has a positive slope, and we know that the function is increasing there. Our question is not just is it positive, but exactly, precisely, what is the slope of this tangent line? Is it 61 miles per hour? Is it 72.5 miles per hour? That's what we want to be able to get to. We have to figure out a way to do that. That will be the next video.